Hello, this is the next video in the series on open channel flow, associated with what I have as lesson 20. And we concluded the last one with Manning's equation for calculating flow, which in US customary units is 1.49 over N, A, R to the 2/3 power, S to the 1/2 power, and in uniform flow we use bottom slope. That's US, and in SI it's 1 over N, A, R to the 2/3 power, S to the 1/2 power in SI. And sometimes this methodology of calculating a discharge in a channel, when we know the bottom slope and we know the cross-sectional flow area and the hydraulic radius, so those are properties of geometry, it's called the slope area method, the name coming from the slope in the area, of course. I have a couple of illustrative example problems that we can use, and we'll do them by hand and then again by computer. So suppose we have a triangular channel with a 45-degree angle, and the flow depth is 1 meter, planed wood. The longitudinal slope, so if we looked in the channel sideways, that's this slope. Longitudinal slope is 0.0019. What is the discharge? There's our problem. Alright, to answer that, we first need to find a value for Manning's N. So Manning's N for plain wood is 0.012, and we looked that up in table 15.1 on page 561 of the 10th edition of the textbook. We also can look it up online. I'm going to do that right now. Go to our class website. Go to the toolbox and open channel hydraulics, and we can, really doesn't matter. Here are some Manning's coefficients. We look on this and we don't have really any guidance for wood, but here's some other ones. And constructed canal, planed wood, somewhere between 0.01 and 0.014, and we'll use 0.012. So that's where that number came from. The cross-sectional area is, in this case, equal to the depth squared. Since it's a trapezoid, we could use the trapezoidal formula y times b plus my. B is equal to 0, there's no bottom width, and so this is equal to my squared. M equals 1, so the result is y squared, and the numerical value of y is 1. The wetted perimeter, again using the trapezoidal formula, is the bottom width 2y square root 1 plus m squared. Bottom width is equal to 0 because there is no bottom width. 2y square root of 2. Y equals 1. That implies that the perimeter equals 2 root 2. Hydraulic radius, by definition, is area over the wetted perimeter, which is 1 divided by 2 root 2. We can calculate the flow rate now as 1 over 0.012. Area of 1 meter squared. 1 over 2 root 2 to the 2/3 power. Bottom slope to the 1/2 power for a value of 1.82 meters cubed per second. Let's try that using the online calculator, whose purpose in life is to help us check our work. Go go to our online calculator, and we're going to need new window, toolbox, channel. I'm going to use trapezoidal channel calculator. Now, even though this says feet, it actually doesn't matter. It's any length unit. So our bottom width is 0. Our side slope is 1. Our other side slope is 1. Our flow depth is 1. We hit the submit, and we now have what we're going to need is going to be the wetted perimeter. So 2 root 2 should be 2.82 feet. Go to my other one. Manning's we go. Manning's in. 0.012. Flow area, 1 square foot. Perimeter, 2.282 meters. Slope, 0.0019. Hit the compute key, and we get a value of 1.816 meters cubed per second. That should be cubed, not squared. All right, so slope area method is a common enough thing. That's why these little online calculators were created. We can look at one more example. We can have a rectangular channel, bottom width of B, flow depth of Y, and S0 is 0.001. This is problem 15.7 in our textbook. Bottom width is 3 meters. Y is 1.5 meters. Plain wood, but essentially we're going to use the same Manning's in. Find Q. By slope area method, Q is 1 over N, A, R to the 2/3, S to the 1/2 power. Area is BY, which is 3 times 1.5. which is 4.5 meters squared. That doesn't sound right. The wetted perimeter is 3 plus 1.5 plus 1.5. 3 plus 2 times 1.5, which equals 6 meters squared. Hydraulic radius, area over wetted perimeter, 0.75 meters. And we can now calculate Q as 1 over 0.012. 3 times 1.5, which is the area, 6 to the 2/3 power, 0.001 to the 1/2 power equals 9.78 meters cubed per second. We can check our work again with our online tool. So rectangular, bottom width is 3, side slopes are now 0, and flow depth is 1.5 units. Hit the submit. Apply slope area method. Flow area is now 4.5 square meters. Perimeter is 6 square meters. Slope is 0.001. And discharge is 9.78 meters cubed per second. Again, there's still this error in the units reporting. We could also do this problem using a Darcy Weisbach approach. So say for instance that K sub s over 4 times the hydraulic radius is 0.333 times 10 to the minus 8th. We would now need to guess a friction factor, so we'll just make a guess of 0.016. We're now going to solve for velocity based on that friction factor. 8 times 9.8 over 0.75 for the hydraulic radius, bottom slope 0.001 over the friction factor 0.016. It gives us a velocity of 1.92 meters per second. Now we need to look up a Reynolds number. The Reynolds number is 4 times 0.75. It's the hydraulic radius. Times the velocity, 1.92, divide by 1.31 times 10 to the minus 6, which is the viscosity. We have a Reynolds number of 4.4 times 10 to the 6th. Now we'll use this Reynolds number and this roughness height in an attempt to find the next estimate of friction factor. Recall this one was just a guess. We'll go back to our online calculation tools. In this case, we have Reynolds number, we need a friction factor. So friction factor needs to know the hydraulic radius, which is 4 times 0.75, the value of 3. Roughness height is 0.333 E minus 8. And the Reynolds number is 4.4 E6. Hit submit. And it estimates a friction factor of 0.009. We now use that friction factor, make our update guess of velocity. So let's see, I'm running out of paper, but I found some more right here. So now we have a friction factor of 0.009. Calculate a velocity, which is the square root of 8 times 9.8 0.75, 0.001, divide by 0.016. You can go ahead and get a calculator up and running for that because I don't happen to have one. But I do have our studio, RM. Okay, so I have an empty workspace. I need velocity is a function of hydraulic radius, slope, friction factor. And we have velocity equals square root of 8 times 9.8 times radius times slope. That's divided by friction factor. Go ahead and get everything grouped correctly. That should be my nice velocity function. List things, sure enough it's there, and now we have the ability to calculate velocities. So we'll just check with the last one. We know that the radius is 0.75, slope is 0.001, and the old friction factor 0.016. Good, that's working correctly. Now we want to put in our new friction factor, which is 0.009. We get a velocity of 2.55. We're now going to need a Reynolds number based on that velocity. We go back here. We have a Reynolds number computer. Forgot to write my velocity down, 2.55. And what we do over mu. Okay, so my diameter is now going to be 4 times 0.75, which is 3. That's the hydraulic radius times 4. The value of velocity is 2.55. I'll put a density of 1. I'll put a viscosity of 1.31 E minus 6. So that gives me kinematic viscosity. Hit that, I get a Reynolds number of 5.8 times 10 to the 3, 10 to the 6. 5.8 times 10 to the 6th power. With that information, I can go get a friction factor. Value for diameter is 3. Roughness height 0.333 E minus 8. A Reynolds number 5.8 E 6. Hit submit. Friction factor is equals 0.008. Go back and compute a velocity. And we would repeat. Okay, so let's just assume, for the sake of argument, that the resulting velocity of this next one is correct. So we now have a velocity of 2.711. Now you would do this until your stuff stops changing. Velocity is 2.71. Yeah. And now we'll just go ahead and take 2.71, multiply that, 2.71, multiply that by the cross-sectional area, which was 4.5 square meters, and we get velocity 2.71, so we get a Q of 12.195 meters cubed per second. And after a few more iterations, it should narrow down to a the velocity and the friction factor will stop changing at some point, or the changes will be small. Okay, so the discharge computed here is 12 compared to the discharge computed of 9.8. So there's a good 20% difference, but by far the Manning's equation method is quite a bit simpler. And that concludes this video, and the next video will pick up with the topic of non-uniform flow.